Hello, welcome to lecture 8. In the last lecture, we looked at a clean solution for implementing priority queue operations using complete binary trees. Priority queue operations are insert and delete max, and I also said you could delete an arbitrary element if you tell me where the element is. Okay, so today we're going to look at implementing search and insert and possibly delete. Okay, this is one of the problems I tossed in the last week lecture, where I said, well, if you just want only search in logarithmic time, keep the array sorted, binary search will do the job. But if I even want to insert an element, binary search, array sorted array has a problem. You have to move elements; it takes linear time. Linked list has a problem, so we didn't know what to do. So then and today we are going to hopefully use, not maybe in this lecture, but maybe in the next lecture, come up with the logarithmic solution using trees. Okay. So again, recall that the heap solution we had for insert and delete max does not support search operation. In particular, if you remember heap, which has max heap, for example, parent greater than or equal to children, and you have a complete binary tree, a heap which is looking like this, doesn't help in search operation, because if I want to search for some element and to know whether it is in my set, I compare with the root, because remember always the root is accessed through the root. I compare it with the root, and if it is smaller, if it's bigger than the root, I know it's not there because root is the maximum element. If it's smaller than the root, then I don't know where it can be. It could be in the left subtree, it could be in the right subtree, and so you literally have to search, all nodes, which results in linear time. Okay, so this is an important observation, that search in a heap can take as bad as linear time, and but that is not a problem, because for priority queue operations, because search was not one of the operations required. We wanted to do only insert and delete max. Remember, the objects are coming and we want to take the highest element and service it. Okay, so now how do I support search and insert? Okay, so that question remains elusive, and we are going to look at it today. And the way we are going to solve it is by sort of capturing binary search method and maybe get some tree out of it, and then we will start from there. Okay, so recall again, if I am given a sorted array like this, and I want to search for element, let us say I want to search for 16, the first thing we will do is we will compare it with 17, that is the middle element, and 16 is smaller, so then I will compare it with the middle element of the left half, and 16 is bigger than 12, so I will compare it in the right subtree and I will compare it with 15, okay, and then I figure out that 16 is not there. Okay. But if I am looking for 23, then I will compare, after comparing with 17, I will go to the right subtree, compare it with the middle, which is 21, and go to the right and so on. So suppose I want to capture how binary search works by a tree, then here is the possible tree. Okay. So I have 17 at the root, 12, 7, 15, 21, 19, and 45. This is again, if you look at it, it's a complete binary tree. It is not a heap because it does not have this parent greater than or equal to children property, because here is a parent which is actually smaller than one of its children. So, it is not a heap, but it's a complete binary tree as the shape of the tree is concerned. So we know that the height of the tree is order log n, and when I want to search for an element, let's say 16, I compare it with 17. Since 16 is smaller, I come to the left subtree because I know anything 16 cannot be here. Then I compare it with 12, and then I know 16 is larger than 12. I compare it with 15, and then I figure out that 16 is not there. But here is a bonus. It tells you that if 16 had to be there, it has to be here. So I can just add it as a right child of 15. No pushing and moving the elements like I would do in a sorted array, and I am seem to be done. So if I search for the element, if it's not there, I just insert it. Okay. Similarly, you can try any number to search for. You will follow the route to a leaf path, and then if it's not there, I will just the search will tell you where to insert it. I'll just go create a node and insert it there, and because of the height of the tree is log n, we seem to have solved the problem of supporting search and insert in logarithmic time. Actually, no. Why? Because the tree when it started off looked like a complete binary tree, but now when after I inserted 16, it's no longer a complete binary tree. Well, you might say, no, it looks pretty close to a complete binary tree. I mean, why did we care about complete binary tree? Because that's what guaranteed us height to be order log n. But now this looks somewhat close to complete binary tree. Is that a problem? Well, it's not even close, because let's say I keep doing these insertions. Remember, I'm not doing one insertion, one search. The problem of the data structure is that I have to set it up in a way that every operation I want to be able to support in logarithmic time. In a heap, after an insertion, the tree continued to be a complete binary tree. That was nice, no problem. But here, so whatever shape you are setting it up, after insertion delete max, that shape needs to be maintained to ensure all the properties, nice properties you had. But here it is not there. In particular, let us say now after I insert 46, I will follow through the the search tree, and then I come here, and then I will realize that 46 needs to be added here. Then I add 49, I will add here. Then maybe an insert says add 48, then you will insert here. And quickly you see that the tree is actually degenerating to be some sort of a linked list. It is no longer a complete binary tree, so you no longer have this nice property of logarithmic height. So we have not solved the problem yet. So this is something to note, and so it turns out you need something more than, so complete binary tree was something too much to maintain. It was okay when we were doing heaps, but when I wanted to do binary search tree, it was too much to maintain because insertions are happening at arbitrary places. Okay, so we need more work, but before I get on to what is that additional property I need, let us capture this property of the tree what I have. Takes us to this notion of binary search tree. So this is something which a tree which captures some essence of binary search algorithm, and so let us look at that tree which I drew today, drew before, and understand what is the property of this tree. Forget about the structure of the tree, it is no longer complete binary tree, we will worry about how to fix the structure, but how are the values distributed on the nodes of the tree. So one thing to note is that value at a node is less than or equal to value at its right subtree. Right. So if you take any node, so in particular let us say root, 17 is less than or equal to anything on the right subtree. and similarly it's greater than or equal to value at left subtree. When I say value at left subtree, what I mean is value at any node in the left subtree. The elements don't repeat, then its value at any node is strictly greater than values of the left subtree, and value at a node is strictly less than values of the right subtree. If they repeat, it can be less than or equal to. Okay, this is the property. This is sort of like the heap property we had, where value at a parent is greater than or equal to value at its children. We are not insisting on that, but we are insisting on the value at the node is less than or equal to value at its right subtree and greater than or equal to value at its left subtree. Okay, so what is a binary search tree? Well, it's a binary tree, which means every node has at most 2 children, and it is a search tree. Typically means what I said before, for every node x, value at x, what I mean, you're storing values at the nodes of the tree is less than or equal to value at any node in the right subtree of x, and it's greater than or equal to value at any node in the left subtree of x. Okay, so this is what is a binary search tree. It's a binary tree where the values are stored on the nodes of the tree with this property being satisfied at the satisfied by the values. Now, what good is a binary search tree? Well, first thing, okay, so you saw some example. So here, this was an example. It's a binary search tree. If you pick at any node, so for example, if you pick at 49, anything to the left is smaller than or equal to 49, anything to the right should be greater than or equal to. You pick 21, anything to the left, in this case it's only 19, and anything to the right is greater than or equal to. So, what are some observations? If I want to search for a node x, search for a value x, how much time, what is the algorithm and how much time does it take? Well, the algorithm is simple. Tree, so you can always access it only through the root. Compare your x with the root, and if the element x is smaller, then if it's equal, then you found it. If it's smaller, then you know there is no point in searching in the right subtree, because the way we have set up the search tree, anything on the right is greater than or equal to that node. So you go search the left subtree, and if it is bigger, search the right subtree and continue this procedure. Very similar to the binary search tree, binary search algorithm, except you don't, I mean, you don't know whether the root is like at the midpoint or not, right? So, for example, here is another binary search tree. So, this is a binary search tree. It satisfies all the properties what I said, but it's not a nice binary search tree. Well, you understand what I mean by nice, we'll get there. So, how much time now search takes is proportional to the height of the tree. Okay. Similarly, insert, which says if x is not there, insert it into your set, will also take time proportional to the height of the tree. Right, this is a binary, in a binary search tree, search or insert takes time proportional to the height of the tree. So, somehow if you can make sure that your height is order log n, we have achieved the goal of supporting both these operations in order log n time. Complete binary tree was one such tree, but that was too much to maintain, because when I use complete binary tree after insertion, the tree no longer remains complete binary tree. I needed to do some more work. Okay, so we have really still not solved the problem of supporting these two operations in logarithmic time, but here is a start. There are some more observations about binary search tree. If I do an in-order traversal of a binary search tree, okay, think about it for a minute before you see what I am going to write. That recall what an in-order traversal is. This is something you looked at in 6th lecture of this series. You visit the left subtree first, and then the node, and then the right subtree, right? How do you visit the left subtree? Well, recursively do an in-order traversal of the left subtree, and then the root, and do an in-order traversal of the right subtree. It's not very hard to see that what you get is a sorted order of the values. This is a very useful observation. Okay, I'm going to verify or prove rather. This can be proved, by induction, because you know that you do an in-order traversal of the left by induction. All the elements on the left are given in sorted order, and then you are going to visit the root, and then you do an in-order traversal of the right by induction. That will be in sorted order. Okay, and because of the property of the search tree, you have the entire thing in sorted order. Okay, so I'm going to say observations 1, 2, 3, 4. Let's talk about in-order successor of a node. Or even a predecessor of a node. So here is my search tree. I am at this node. It gives me some value x. I want to know in the in-order in-order successor, meaning whose the element whose value is immediately larger than x. That's the in-order successor. And who is the value who is immediately before x? That's the in-order predecessor. So in the sorted order, who comes after x is the in-order successor, and who comes before x is the in-order predecessor. How do I find that? So it's easy to see that, okay, I'll just do it for successor, or maybe even not even for completely successor, but if x has a right child, then in-order successor is the smallest element in the right subtree. I mean, why am I talking about in-order successor? It will be clear later when I talk about something else. So it is the smallest element in the right subtree, and how do I find that? Well, I just go to the right child and go left, because by the search tree property, the smallest element will be in the leftmost leaf of the right subtree. Okay, you can find that. And now I'm going to say if x has no right child, I'm going to let you think about it. Who would be the in-order successor? Very interesting question. Okay. And in a very similar way, in order predecessor is something you will find by, if x has a left child, you take the largest element in the left subtree by traversing the rightmost path, and you will get the in order predecessor. If x has no left child, what do I do, right? So I'm going to just say similar questions for in order predecessor. Okay, something for you to think about. But I mean, if it has a left child, it's easy. But if it doesn't have a left child, who is the in order predecessor? Okay. Do some examples of the search tree. Write down the sorted order. Look at the in order predecessor, successor, and in the tree, who would be the predecessor, successor? Think about it. Okay. Now, why am I saying all this? Well, we saw that the search in a search tree takes order height of the tree. Insert takes order height of the tree. A natural question is, what about delete? It turns out delete is also a very natural operation. You need it in any database. Not only you want to search for an element, you also want to add elements, you want to delete elements, and you can also do delete in a search tree in time proportional to the height of the tree. And I'll give you a very brief description of how you would do delete. Okay, I'm going to give a pictorial description. So, your user comes and says delete x. First you have to search for an x. So you will start from the root, follow through your search tree path, and let's say I found my x here. And the request is to delete x. So there are three cases, okay. If x is a leaf, life is simple, just delete it, done. Okay, there is no one way to do it. I'm just going to give you one particular way. So if x is a leaf, well, it will be a leaf. You can just delete that node, adjust the parent pointer, and be done with it. If x is not a leaf, then it has at least one child, either a right child or a left child or both. Okay. So what I'm going to do is, if x has a right child, replace. So now I'm going to say, okay. So I'm intermixedly using x as a value as well as a node. Hopefully from the context you can make out what I mean. Okay. So here when I say if x is a leaf, I'm talking about the node x. So if x has a right child, replace x by its in order successor, which you know how to compute. We talked about it, right? So if x has a right child, there is an in order successor y. So I'm going to take that value y and put it here. X is gone now, and delete y. Okay, it's a recursive call. How do I delete y? Apply the same algorithm. If y is a leaf, it's done. Otherwise, do one of the two things I'm going to tell you. That's it. It just continues. And if x has a left child, like x is no right child, but if x has a left child, I know one of the two should happen. Replace x by its in order predecessor, and delete y. That's the entire algorithm. Okay. You want to delete, some value in a binary search tree, first find it by doing your standard search algorithm. If it is a leaf node, delete it, you are done. If it is not a leaf node, it has either a right child or a left child or both. If it has a right child, find its in-order successor. I just defined you what an in-order successor and how to find it. Take that value, put it in X, and then go your surgery, the deletion at that in-order successor node recursively. If X has a left child, replace X by its in-order. Okay, so maybe I should say else. So if X has a right child, you are done, right? You would follow that path and be done with it. If X has no right child, then you look at if X has a left child, it should have because it's not a leaf. Replace X by very similar. Maybe I should give a different name for. Okay, so this is the entire algorithm. How much time does it take? Well, again, time is proportional to height of the tree. Because we are just traversing one path from a root to a leaf, that's all. You just keep going down, you don't go up and down. So you just, as we come here and then keep going down. So in summary, what I have told you is that in a binary search tree, which sort of captures and starts its inspiration from the binary search algorithm, insert, search, delete, and actually there are a lot more operations, join, split, there are a number of things you can do, can be done in time, order, height of the tree. We are still not done with our goal. We want to achieve all of these operations in logarithmic time. So now our new problem is how do I make sure that the height of the tree is order log n? If you really want to make the height to be order log n, that's not too difficult. We know a complete binary tree can do it, but the challenge is that you have to maintain it after insert and delete operations as well. Maintain whatever structure that is. That's the challenge. Okay, so we'll talk about that in the next lecture to achieve our main problem, main goal of supporting all these operations in logarithmic time. Okay.